Okay, it's 11, so it's my pleasure to introduce our next mini-course lecturer, Matija Bucić, who's currently an assistant professor at Princeton University. However, in about a month and a half, he's taking a tenure-track appointment at the University of Vienna. Matija is native of Croatia. He got his bachelor's degree at the University of Cambridge in the UK, and then PhD in 2021 in ETH Zurich, under the supervision of Benny Sudakov. Upon completion of his PhD, he spent his postdoctoral years in Princeton, splitting an appointment between the Institute for Advanced Study and Princeton University, and then he got an assistant professorship in Princeton. Matija's main research expertise is extremal and probabilistic combinatorics. However, he has kind of wandered into neighboring fields, such as discrete geometry and Ramsey theory. And Matija's course on sublinear expanders, a notion that has been instrumental in many recent advancements in the field, in particular his breakthrough work with Richard Montgomery on the Erdős-Galai cycle decomposition theorem. And without further ado, Matija.
Thank you very much, Wojtek, for the kind words and the introduction, and thank you all for coming. So just to give maybe some initial organizational things. So the course the lecture notes will follow the template that Imre set last week. So after every lecture, we will post a bit after the lecture notes will be posted for whatever we covered that day. And the problem sets will not follow his example. So the problems will kind of be tied in through the course. So at various points when there is a kind of cute aside or a chance for you to redo the argument I showed you and kind of to make sure you understand it, I will just mention it and put it as an exercise, and it appears in the lecture notes in the kind of correct place of where it fits in the flow, rather than being collected at the end. So also I have a wonderful TA, Domagoj Bradac, who is hiding somewhere. Yeah, he's waving there. So he's an amazing, just finished grad student from ETH, so my academic brother. And he arguably has possibly even more papers using this than I do. So please do feel free to pester him as much as you want. And sorry, Domagoj, but yes. That's, I think, all about the organizational stuff. So also this course is a little bit different than I think most of the others that you have during these 3 weeks. So it's because it's about a tool rather than about kind of a big area or an object. So, well, there is plenty of interesting stuff that people studied about sublinear expanders in this course, and generally I don't particularly intrinsically care about them. So the reason I care about them is because they are useful to attack a lot of other problems. So the goal here is not to show you beautiful properties that these things have, but to show you useful properties that you can actually use for various different problems. So also we will start with a kind of brief introduction also to expanders, because I don't want to assume that you know what they are. So actually just to get a feeling, how many people here know or have some idea what an expander graph is? Great. And a sublinear expander graph? Okay, that's more scary. We'll see. So I do want to still take it slow and kind of build up to it. So I know that quite a lot of people in the audience have taught and worked and used this. They have been used for a lot of different things in the last couple of years, and maybe last 10, 15 years, we could say. So for the people who are kind of familiar with the stuff that we'll mostly be touching upon today, here's an open problem. Which I like a lot, and which is kind of touching upon a lot of different things that we will see throughout the course. So it's due to Matušek, Privetti, and Škovron from about 2006. And it comes from a geometric intuition, but this is just a translation or reduction to a graph theory problem. And so it's known if you add the log n factor there. So if you want something that people already know how to prove, and that you should be able to prove, hopefully, with the stuff that I'll show you throughout the course. But I think the n log n is very interesting. And if anyone has ideas, I'm happy to think about it. So if you are bored, there's something for you to do. Yes? Yes, thank you. And please do correct me, and I am prone to typos. Very good. Any questions other than this excellent one? OK, good. So let's start, as I promised, with kind of general, mostly expander graphs. So for now, let's forget about this. We'll get to it soon. So first, let me give a kind of intuitive way of thinking about this. So expander graphs are very robustly well-connected graphs. Now, there is actually plenty of interpretations of both robustly and well-connected. And actually, there are plenty of definitions of expanders that sort of tie into all of these. But just to have something slightly more concrete in mind, maybe let me just put that for this. I mean that there is any two vertices are close, meaning there is a short path between them. And by this, I mean this remains true if you delete some stuff from the graph. So this remains true. On minor modification, let's put it that way. And I mean kind of you delete a few vertices or edges, and you still want that everyone is close to everyone. So I want to just start with a high-level definition just to kind of have some feeling of what these things maybe are. And also just because this lets me illustrate one actual concrete applications of general expanders, well, which is that they're actually quite nice for building communication networks. Why? Because if you have a network in which any two nodes are close, that's quite good for you. And also, if you can keep that even if a storm destroys part of your network, that's also very good for you. And the second part that we'll mention in a moment is that you can build these with very few edges, which means it's also cheap to build. So they actually are used also for chip design and networks. So they are used all across computer science, both applied and theoretical. They're also used quite a lot in mathematics in various different areas. And here, the basic thing is that actually quite a lot of auxiliary graphs you can construct from various objects have these expansion properties. So kind of they have been studied extensively, and people know a lot about them, and you can translate and use these things. So that's the kind of general blurb about expanders. So let me, so how far along here do you see? People start complaining once my hand stops being visible. I know it also depends on the distance, okay. So let's start with, so let me give you a concrete definition. So this is usually called vertex expansion. And it's sort of the namesake definition where they came from. And there are, as I said, plenty others which are more or less equivalent. You can switch between them by paying maybe a little bit. But mostly, we will really be focusing just on this one and closely connected edge expansion ones. So for every epsilon bigger than 0, and n vertex graph G is an epsilon expander if for every subset of its vertices, which isn't too large, which at this point I'm just saying it should be size less than a half, its external neighborhood in G has size at least epsilon times the size of the set that you expanded. So let me write what I mean by the neighborhood, the external neighborhood. So ng of u is just all v in the graph G, not taking the stuff from U. I'll comment on that in a moment, such that Vu is an edge of G for some U in U. And swap these. OK? So let's draw a picture. Here's our graph G. Here's an arbitrary subset U of its vertices. We don't want to take it to be bigger than a half, and I'll get back to that point in a moment. But what I want from it is that if you take one step out, just one step out, what you see is kind of comparable in size to u. So it has at least epsilon times the size of u extra vertices that you'll get. OK? So that's the basic vertex expansion definition, which probably most of you who raised your hands initially have seen in one form or another. So let me just comment a few things that will sort of be important for the sublinear perspective. One is that we're working with external neighborhoods. So this is slightly different than what Yin Yang was doing if you took her class last week. So that means I'm not including the vertices of u inside of our neighborhood. For usual expanders, this barely makes a difference because you usually have a kind of big constant factor expansion. So whether you have C or C minus 1 expansion, it's rarely important. But we will be working with these expanders where this epsilon is tiny and even tends to 0. So for us, this plus 1 is a massive difference. And it's an important point that we only ever, whenever I say neighborhood, I really mean the new vertices, not the ones that we've seen already. Just makes the numbers a bit nicer. That's one point I want to make. The other point I want to make is the restriction on not expanding the whole set. So as I said, right, if you try to expand the whole graph with this definition of external neighborhood, you just don't have space to find new vertices. And you'll see that usually this is not such an important point, and we'll see very soon a lemma that kind of illustrates what I mean by that. So this is not a big restriction, but for technical reasons, it needs to be there. And sometimes you sort of need to bypass the fact that you are not allowed to try to expand super large sets, at least with this definition. Also, I want to point out that with usual expanders, people would usually put here something like 1 plus epsilon or epsilon, so that you can actually get expanders which are better than 1 expanders. Because if you think about the definition as I wrote, if you try to expand a set which is half the size, the most it could expand is by a factor of 1. And we have much better expanders than that if you think about GNP or KN. So these are some examples I wanted to mention. So when working with usual expanders, you want to tweak this a little bit more. And again, it's not really all that important, because if you put something like n over 2 epsilon, and you expand a set of that size, because you'll get epsilon many new vertices, you reach more than half. Right? So in the usual expanders, it's just the technicality of space that works a bit differently than for the sublinear ones. For us, you can forget about everything that I just said. It will never be important for this course. Very good, I think. First one, as I said, kind of the best expander you could possibly have. Well, just take a clique. Right? Is there a better connected graph than a clique? Well, of course not. So what it has as a downside is that it uses a lot of edges. So if you think about kind of building these efficiently, it's expensive. So an example class which actually includes the clique, and an important one for various reasons, is GNP. And there is, of course, some sort of restriction on P when you want it to happen. But this I'm leaving as the first exercise. So exercise 1, work out expansion properties of GNP. As P varies. So I'm deliberately leaving this vague so that you can choose how much you want to do and to what level of precision and understanding, etc. But I just want you to play with this and understand why the binomial random graph GNP actually has this expansion property. So if you haven't done anything with expanders, this is a good exercise to do. For us, they are pretty good for building intuition, because they are actually very, very strong expanders. So you get lots of nice properties in them that you will not get in the sublinear world. But still, they show you some sort of goals and some sort of properties that you might try to emulate and try to prove for sublinear expanders. So it's not a bad thing to think of these as like weakly random graphs, quasi-random graphs if you want, with a very, very vague and weak notion of weakly. Very good. So everything so far has been about mostly usual expanders. So these are all at least constant factor. So I want to first show one lemma which applies in both worlds, but still technically I want to leave it in the general expander world. And this is called the diameter bound. So it's a very standard thing, but it's going to explain my intuitive part that any two vertices are close in an expander, because from this definition, it's maybe not immediately clear why these two have anything to do with each other. And it's a lemma which is actually very useful usually you need to tweak it a bit, and we'll see that, and it will be reappearing throughout the course. But yeah, I've missed the diameter part. But it's a rather simple thing, but a cute little lemma, and I want to do it since we will be using it or versions of it again. So probably later on I will just say by the same argument behind diameter bound you can do something. So I want to show it once when it's easiest and cleanest. So let epsilon be bigger than 0, G and n vertex epsilon expander. Then diameter of G is at most twice ceil of log base 1 plus epsilon n over 2. And I'll not be that precise in the future, but let me at least one hopefully write correct lemma on the board. So what's the diameter? Just to make sure. So it's the maximum distance between two vertices. And what's the distance between two vertices? It's the shortest length of a path that joins them. So really, this lemma captures that intuition that in an expander, for any vertex, you don't need to take that many steps to reach any other vertex. Okay? Good. So the proof is reasonably simple. Well, very simple. Maybe I can start here and progress there. So let me just get rid of this monstrosity that I wrote there. So let L be this ceil of log 1 plus epsilon n over 2, just so I don't need to rewrite it again. And what are we trying to show? For any u, v in vertices, there is a path of length most 2L. Or let me actually switch it immediately into a walk, and VU walk. So let me erase the other board and draw a picture, and then a few more steps and we get the lemma. Right, so here's our expander graph G. We pick two arbitrary vertices inside of it, and we want to find a short walk between V and U. If you have a short walk, you have a short path, so I'll not make that distinction too much. So now, the only information we have about it is the stuff that I just erased, which is somewhat unfortunate, but is that subsets expand, right? If you take steps, you grow. So a sort of sensible thing to try to do is, well, let's look at V, and let's grow. So let's look at its neighbors, and then let's look at its second neighborhood, and so on. So we just draw these balls going around. We kind of reach more and more of the graph. Now, ideally, we would like to hit U, right? But we get this nice fast expansion by 1 plus epsilon factor only up to n over 2, right? So that was this nonsense condition that we need to deal with occasionally. This is an example where you kind of see that it's not hard to deal with, but you do need to deal with it. which means that once you hit more than n over 2 vertices, well, now you no longer actually, well, you can't really use the same expansion. So from that point, maybe you are super unlucky and you need to take a lot of steps to reach your U. So the trick that kind of reappears and is used quite a bit for this type of things is, well, let's stop once you reach more than a half, and let's do the same from the side of U. Okay? So again, take its neighborhood, second neighborhood, so on, so on. We know that in relatively few steps you reach more than half. Right? So now, because both of them reach more than half, there is something in the middle, that in the intersection. And between this and this, there is a short path. Between this and this, there is a short path. So between V and U, there's a short path. That's the whole proof. So let me actually write some things. So, so let me actually define something that will also be showing up a lot. So the ball of radius r around the vertex in G is vertices reachable by paths of length at most r from V. Right, so these are the balls that I was drawing there. They will kind of be reappearing. You can also think of them as second, third neighborhoods, etc. Although now this notion of external, internal starts to go in the way. But ball is, I think, the kind of the correct way of thinking of them when you do this expansion business. Very good. So now the claim that I made before was that if you take a ball with that balls grow very fast up until you reach half of the vertices. So ball of radius L in V, of V around V in G, has size bigger than n over 2. That's a claim. Now L is, remember, this log monstrosity there. So we'll now see where it's coming from, because it's sort of immediate. So you know that for every I, size of ball of radius I plus 1 around V is bigger or equal than 1 plus epsilon times the size of the ball of radius I around V. Why? Well, if you have your ball I, the ball I plus 1 is obtained by taking one step out. This is precisely what the expansion condition tells you. And it tells you get epsilon new vertices in your external neighborhood. So in total, your size grew by 1 plus epsilon because we're keeping the old ones as well for the ball stuff. Unless, so what's the caveat? Unless this one's too big, right? So unless this thing is, okay, let me not do it that way. But if that happens, then we're happy already, right? Because that's the bound we're aiming for. So if the ball is already of size n over 2, well, we have nothing to do. It's already big enough. So now that means if you iterate on its own, you'll get that that the size of the ball of radius L is 1 plus epsilon to the L. And this is where that nonsense is coming from. So ball of radius L around V has size bigger than minimum of 1 plus epsilon to the L and n over 2. And we're done because this is also bigger or equal than n over 2 by our choice of L. Okay? So now this gives us the claim. If you take L steps, you reach more than half. So now we just conclude. So ball of radius L around V, and ball, because we can repeat the same argument around U, are both bigger than n over 2. So there's a vertex in the intersection. And that means, just by definition of VW being in the intersection, that there exists a VW walk of length most L, and there exists a UW walk of length at most L. Put these together, you get a UV, you concatenate is the word, UV walk of length most to L, and we're done. Right, so it's a rather simple thing. Like, the good trick to remember from here is that you need to be careful about expanding large things, but it often is helpful to kind of expand from two different sides. So we'll see that show up quite a bit, and this was just a kind of simple illustration of that happening. Very good. Any questions about this? Okay. So now, let me maybe leave the statement for a few more minutes, but let's delete the rest. So now I want to start actually talking a little bit about sublinear expanders. So again, first informally, a sublinear expander is an epsilon expander with epsilon tending to 0 as n tends to infinity. So what I mean by that is really just we're going to look at a weak version of expanders. So what people are mostly used to is that your expanders grow by at least a constant factor, preferably a big constant factor, preferably even something bigger, and then you get amazing stuff about these expanders to hold, mostly inspired kind of by GNP, which has all of these properties unless P is really tiny. So what we are going to do instead is we are going to look at the weak version. So now where you get very, very small expansion. So now the kind of sensible question is why? And I already hinted a bit at the beginning. It's because these things sort of show up everywhere. So if you think about Gn1/2, it tells you that expanders are, like, most graphs are expanders. If you take Gn1/2 and you show it's an expander, right? So arguing about expanders gives you statements that hold for a typical graph. For sublinear expanders, they actually allow you to prove stuff for all graphs. And the reason for that is because you can find one of these things with appropriate epsilon, which I'll get to in a moment, inside of any graph. And moreover, you can even decompose graphs into these type of things. So they allow you a kind of, and a very often very powerful way of understanding an arbitrary graph. Now, of course, what I mean by finding one of these, I also want to preserve some sort of average degree or some sort of other properties of the big graph, because otherwise, technically, a single vertex graph is an expander, and decomposing a graph into single vertices is not so impressive or useful, I think. But yeah, so this is the whole point of the course that we'll be getting to. So I'll show you a path to expander lemma, hopefully also a bit later a decomposition lemma, and sort of how to use them. So I also want you to think of, just to have a concrete epsilon in mind. Yeah. Yes, thank you. I warned you that I make a lot of typos. Very good. So, right, so just to have a concrete epsilon in mind, a good one to keep in mind until we kind of specify a bit more precisely what's going on here is epsilon being 1 over log n. So this is sort of the threshold at which you start being able to find them in any graph and decompose with 1 over log squared n. And this log squared n can probably even be pushed, but I never actually needed it. Or it's actually CS people who like the decomposition lemmas more. So if you want the strongest decomposition lemmas, you should look at the CS literature. But in terms of path to expander lemmas, this is sort of the threshold at which you will be able to find one. And if you think about it, 1 over log n isn't such a bad expansion. So if we go back to the proof of this diameter bound, we never really cared about this epsilon being a constant. you can choose it to be 1 over log n at the beginning, and the exact same argument continues. So what it tells you is that in this case, the diameter of this type of expander is at most, so big O, let me get rid of the seals and stuff, log 1 plus 1 over log n times n, and let me also get rid of the half, right? And now this is log n divided by 1 plus 1, log of 1 plus 1 over log n. Since this is small, log 1 plus x is roughly x. So this is log n divided by 1 over log n, so this is just log squared. Again, takes a bit of computational steps, approximations in between, but nothing interesting. So this tells you that these things still have a small diameter, right? It's not quite as small just being a log as we had for constant factor expanders, but it's still polylog and it's still reasonable. And unlike usual expanders, you can find these sort of everywhere. And we'll see soon that actually, if you kind of do a bit more careful definition of these things, you can get this with log n, log n, so you can even get much closer to just the log n world there. Very good. So I also wanted to just mention here that this diameter bound is a good thing to use to kind of estimate how good your expanders are. So in terms of how well they expand, because very often you get these definitions which are not quite as clean as what we are working with. So they can, expansion of some sets, not of others, and various variations of that idea. So generally speaking, this is a very good way of figuring out how good your expander actually is. Because the diameter tells you how long you need to expand to see the whole graph, essentially. And this is something that most of the problems will actually require you to see. So this is also why you will see this log n, log n showing up in a bunch of results, because that's the diameter we can show for the kind of best version of these sublinear expanders that I know of. Very good. Any questions so far? OK, so the second lemma I want to show is actually quite often quite useful. It's cute. And it says that if you have, so we'll stick with the 1 over log n expanders to have a concrete expansion function, but you can do it for any. It tells you that these expanders have long cycles and paths. Now, if you think about it, this is a very old question in extremal graph theory. It goes back to Dirac, what kind of conditions you need to find long cycles. And it tells you need to be very, very dense to guarantee a Hamilton cycle. And there's been a lot of work in the area trying to kind of figure out if there are some conditions which allow you to find Hamilton or long cycles, even for much sparser graphs. Actually inspired a bit by the idea that for GNP, you get a Hamilton cycle way, way lower. So actually, most graphs have a Hamilton cycle. Right? You don't need density n over 2 in GNP to find a Hamilton cycle. This is an old result of Bela, which tells you the threshold, and it's around log n, a bit over, but not relevant for now. And so the idea is most graphs have this. So can we find some nice properties, or can we identify which properties actually guarantee these long cycles? So there was a recently resolved very nice conjecture of Krivelovich and Sudakov about expanders having Hamilton cycles. So this is a pretty big result that was recently proved. And there is also an open problem of Babai and Lovas about vertex transitive graphs of Cayley or Cayley graphs. So that goes in the direction that actually symmetric graphs should also have this type of things. So both these results are kind of getting to the idea that actually both vertex transitive graphs and random graph and ND lambda graphs, and these are expanders, they have some expansion properties. So actually expansion is something that drives and lets you find long cycles and paths, at least to some extent in all of these things. So let me show you a not quite as strong a lemma, something simple, and in part because it lets me illustrate a very cool method of Ben Eliezer, Krivelovich, and Sudakov called the DFS method. So it's not just DFS algorithm, but applied in a specific way. And show that in these type of expanders, you will be able to find a long cycle or path. So this is something we'll also use a bit later in the course, and it's maybe a good thing to get used to these type of things. Also illustrate some other ideas. So let me actually write the lemma. So any n vertex 1 over log n expander, and again you can put here whatever you like. Has a path of length omega n over log n. It's not quite a Hamilton path, but it's a linear length path. Well, I mean, not linear, but n over log n. And you will have as an exercise to show why this is tight. Has a path of and the cycle. So here we will lose another log. This is not necessary, so you will have an exercise to get also n over log n bound for the cycle. But the proof I want to show you for this is, I think, a bit more instructive and a tiny bit simpler than the n over log n one, so I'm doing that. And it will use this as a first step. Okay, so you can do this with sort of any expansion, and in the notes I'm pointing you to a survey where this is done very carefully. If you ever just want to use it as a black box, you can quote Michael Survey. He has a very nice version of this lemma. Very good, so let's prove it. Right, so the idea is to use this DFS algorithm, which has been quite useful. I think I have maybe 4 or 5 papers using it in various different areas, Ramsey. So it's very useful for dealing with paths and cycles. And so let me describe what it does. So before writing kind of more formally, let me just kind of do an interactive picture of what the algorithm is doing, and then I'll write a little bit of what it's doing. So we will, at any point, maintain a set of unprocessed vertices. At the beginning, this is essentially everything, or everything except one vertex, which we will take out, and we'll put it in a stack. So this is how CS people like to call it. So initially, there is one vertex in the stack. Everything else is there. We will also later have a set of processed vertices. Now, what the algorithm does is it looks at the vertex which is at the top of the stack. So currently, that's just our V. Looks at the unprocessed vertices. If it has a neighbor there, you put it at the top of the stack. You pick arbitrary one, whichever one you like. You actually can get a bit more power by making careful choices, but we don't need it here, and I want a simple version. Right, so if this V has a neighbor here, I'm going to delete it. So I'm going to delete it here and put it at the top of the stack. Because it was a neighbor, it sends an edge to V. And what will be important for us is that that means that throughout this process, the stack is a path. Okay? So then what we do, now this is our top of the stack vertex. Let's look if it has some neighbors. We find one, we put it there, we delete it there. We keep doing that. At some point, let's say now, so I don't, because I ran out of space, you hit a vertex which doesn't have any neighbors in the unprocessed vertices. Right, so nothing else to add to our path. So what we do then is we pop that vertex from the stack, that's the official terminology, and you put it in the processed vertices. Okay, so I kill this guy, it reappears there. Okay? So this will process all unprocessed vertices eventually and move them into the processed ones. Right, so in each step, either you move an unprocessed vertex at the top of the stack, or you move someone from the top of the stack to the processed vertices. So this one goes down by 1, or this one goes up by 1. We start with everything here. We will end with everything here. Very good? That's the DFS algorithm. So I'm just explaining something rather simple. I'm just pointing out to the fact that because of how we're doing it, at any point our stack is actually a path, which is a kind of nice observation. There is one extra property that I will mention in a moment, but let me just write out what, and just a few more things about this. So we have a state, so this is DFS algorithm. So we have a state of T, B, I think I want to call this S, P, and T. So this is, maybe let's call this U. Unprocessed. This is the stack. This is processed. And this is top of the stack. So now what the algorithm does is if there exists a neighbor of T in U, move it to S and make it T. Right, so this is the step. If we find some neighbor, we take it to the stack, we put it at the top. If not, else pop the T. So technically, I guess you also need to remember the ordering in S, but let me not write that level of detail. Else move T to processed vertices and make its predecessor T. Okay, well, that's a formal algorithm. It does something. So far, it's kind of completely unclear what it's doing with respect to that, other than maybe this observation that we get a path here. Okay? So the key property that I didn't yet mention, I sort of drew it partially there, is that at any point in this process, you don't have any edges between these two. Let me draw that, and then let's see why that's true. So think about it. Whenever we put a vertex into the processed vertices, this was because it had no neighbors inside of the unprocessed vertices. So when we move it here, it is anti-complete. It doesn't have any edges going up. And the process only ever after that removes vertices from here. So it remains true. Okay? So key property. No edges between U and P at any point. I will not write it out. It takes a sentence, and I think it's sort of clear if you run the algorithm. So, and will not be much clearer from the words. Very good. So now our picture maybe looks a bit more interesting. Why? Well, we have these two sets which kind of, well, why am I drawing edges? There is no edges there. I wanted the other color. I forgot to switch the color. Very good. So no edges here. Right? So we have a partition of our graph into an anti-complete pair and the path. But remember, we are in an expander. Right? So what can you tell me about anti-complete pairs in the expander? Yeah. Yeah. So like one of them needs to, like, yeah. So they need to send all of their edges out, right? And you also can assume that one of them is large, precisely as you said, because, well, if they're both tiny, then the path is massive. And this is what we want. Right? So one of them needs to actually be, needs to be reasonably large. And actually how you usually want to do this is, because you can't expand two large sets either, is you want to run this up until these have the same size. Right? So if you remember how this DFS worked, it always either decreased this by 1 or increased this by 1. This starts as bigger and finishes as smaller. So by intermediate value, at some point, they will hit the same size. At this point, these two things have the same size. And it needs to be close to half of the graph, because otherwise you will get that many vertices on the path. And now you can just expand this, right? This is a set of size n over 2. All of its neighbors are on a path, so its size should be at least n over log n. You get a path of length n over log n. Okay, so let me put some words there and let you process. Any questions before I do that? So stop the process when size of u is equal to size of p. Again, this happens because of this intermediate value argument. At this point, iter size of u equals size of p is less than n over 3, which implies, sorry, not p. No, s is the path for us. That was a bad choice of naming. N over 3. So that implies the size of s is at least n over 3, and we're done, right? This is a path. Well, they call it stack, so anyway. Otherwise, whichever one, u is at least n over 3. But also, we know that the neighborhood of u is a subset of S by the key property. So that implies by the expansion, I'm slightly running out of space on this board, that size of S is at least 1 over log n, the expansion factor times n over 3. And we are done with the first half of the statement, right? So S, again, is a path. It has length n over 3 log n. That's what we claimed. OK? So this is a very useful kind of trick. So I'll show you in a moment like a tiny tweak that lets you go from a path to a cycle. So far, yeah, this type of structural thing that it lets you establish that you kind of get this partition into an anti-complete pair and the long path is something that's actually quite strong in various situations. Any questions? OK, so let's do this path to cycle. And this is another thing I'm doing mostly just to illustrate some sort of ideas that we'll be seeing later as well in this kind of simple setting. But also, I mean, it's nice, but you can do n over log n, and you maybe even arguably can do n over log n easier than I will do n over log squared n. But so that's the exercise for you. So let's put exercise 2. Show there is a cycle of length at least n over log n. And also, this is tight. So you maybe exercise 3. It's tight for both a path and a cycle. Show it is tight. I mean, up to constant factor, of course. Very good. So let me now show you. This was not a good place for visibility, I think, but it occurred to me now. Let's see how to get a cycle. So we've already found the long path. So let's forget about everything else. So we have a long path of length n over log n. So what we'll do is we're going to cut it into 3 pieces. Okay. The middle one should have size something like n over log squared n. That means the other two have size n over 2 log n roughly or something like that. And what we'll do is we are just going to delete these vertices from the graph. Okay. So I claim that the same argument that we did for the diameter bound, remains to hold in this graph if you start from these sets. Right? This set has size n over log n. We expand by 1 over log n factors, so maybe I want to put a 4 there, or 2. Right? So when you expand a set of this size, you get at least double that many new vertices. So you aren't blocked. And you can do the same growth, and the growth even happens at the same rate. It's just you lose the factor of a half in each step, which is anyway something we need to live with. So, and that means that we'll be able to find a path that links these two pieces. And once you find the path that links these two pieces, now you remember that you had these vertices there, so you can guarantee that actually it has length whatever you had here. Yeah?
So in this log square, you could have used anything that Komlós passes along?
You need to not be blocked. So if you think about a set of size n over log n, in a 1 over log n expander, it's guaranteed to have roughly n over log squared n at most vertices. So if I deleted n over log squared n vertices, right, then I could cut off this set from the rest of the graph. So you do need like n over log squared n and up to some constant hitting. So that is the, at least kind of, sort of naive way that I'm doing this. You can actually tweak this a little bit to do it n over log n as well. But there is like this is aiming at a slightly different proof that is even simpler than any of this. But anyway, okay. So the reason I wanted to show this, well, I'll write some stuff up, but I wanted to show it because these vertex deletion arguments are at the heart of a lot of arguments that we do with these sublinear expanders. So in a sense, you want to delete some inconvenient edges or vertices from the graph, and then you want to still keep this nice connectivity property that you have from the diameter. So this is a kind of nice example where you can actually do this. So let me maybe write a few more words about this. Right. So cut P into x, y, and z such that size of x, size of z is at least s, yes, thank you, yes. Size of s over 3, and size of y is at most n over, so we got, I guess, there n over 3 log n, so maybe n over, whatever, 10 log squared n. Okay? So now, in G set minus y, any set of size bigger or equal than n over 5 log n, okay, maybe 12, and expands by at least 1 over 2 log n factor. Right? So in this type of graph, you can't really make a diameter statement because like a single vertex might be cut out by this, but you do know that big sets are still linked. Right? And this allows us to find a path between x and z, even a relatively short one. So by the diameter bound-like argument, I need a better name for this argument because it will be showing up. There is a path in G minus y between x and z. And then just take a shortest one, just to avoid self-intersections, etc. And add y to it. Whatever that was. Yep. I need a lower bound on the side. Ah, yes. Yeah, thank you. So I want this free was there. Let's say up to a factor of half. But you're perfectly right, yes. Because this is where we're actually gaining. So maybe it becomes a 24 or whatever. I'm not in the business of constants. Very good. But please do point these things out there. It's very good to point it out. Make sense? OK, so I have about 4 more minutes. So let me end with just stating a definition, or actually half a definition. I would like you to maybe think about a process a bit, because we'll be playing with it next time. And it's sort of going to be the key thing we will be playing in this course. So it's a definition of a robust sublinear expander. So this is something that was introduced by Komlós and Szemerédi in the 1990s. So I should also say they are the first who realized that this type of business is actually super useful. I'll say that again later. But this robust idea, so the definition I'm going to state is not theirs. It's a bit kind of slightly modified to be cleaner and to work for different regimes. This is something that I'll get back to next time when we actually see what we can do with it. Or how to find it. But for now, let me just state the definition. And then we'll start next time from that definition. So an n-vertex graph. So actually, I guess I didn't formally define what a sublinear expander is. So let me do that now. An n-vertex graph H is a sublinear expander. And then we'll add a word robust next time, because we sort of get it for free and it's useful. Sublinear expander if for every 0 less equal than epsilon less equal than 1, and for every u subset of vertices of H, such that the size of u is equal to, let me put equal n to the 1 minus epsilon, although it's actually convenient to put an upper bound there often, but we'll get back to that next time. We have that the neighborhood of u, again, external neighborhood, I'll stop mentioning it, but I do mean it, is at least epsilon times the size of u, and let's say over 4. OK, so I do have 2 minutes more, so let me say a few more words about this. So that's the end of the definition. So what's happening here is I want to define an expander which actually has different rates of expansion for different size subsets. Right? So before we said 1 over log n expander, you always expand by 1 over log n. Actually, what tends to happen for all of these things is it's much easier to get small sets to expand better. And this is what this is trying to capture. So this one says this epsilon parameter is just a kind of clean way of controlling the size. So I allow this epsilon to also depend on n. It's just a number between 0 and 1. So if you choose it to be 1 over log n, then you get that sets of size n over 2 expand by a 1 over log n factor. On the other hand, if your set is actually polynomial size, so n to the 1 minus epsilon with an absolute constant epsilon, then you actually expand by a constant factor. So you're back in the world of usual constant factor expanders there. And you have a smooth transition between these two. Now, one nice feature of this, which is final exercise for today, is prove that the diameter is at most log n log log n. So with just 1 over log n, we got 1 over log squared n, log squared n diameter. Because of this better expansion at lower rates, we improve the diameter quite a lot. And we come close to what you get for the usual ones. So when you are fighting for problems that are close to log n, this is what's going to save us in a few places. So let me stop here for today, and we continue tomorrow. Thank you.